Hello guys, in today's video we are going to see about electrochemical series and its applications. In the previous video we have seen about types of cells, namely electrolytic cells and electrochemical cells, and we have seen how to construct an electrochemical cell in which chemical energy of a spontaneous redox reaction will be converted into electrical energy. And we have also seen how to measure the standard reduction potential of a half cell by connecting it with a standard hydrogen electrode and taking the standard reduction potential of She to be 0. So in this video we will be seeing about those reduction potentials that we have measured using standard hydrogen electrode. So look at this. This is the standard electrode potentials of zinc and copper, which we found by connecting the half cell with the standard hydrogen electrode, and we have taken the value of standard hydrogen electrode to be E naught value to be 0. Now see, when zinc is connected with She, then this acts as anode and this acts as cathode, and I've told you how to calculate the E naught cell. E naught cell is equal to E naught cathode minus E naught anode. So this is taken to be 0. E naught value is taken to be 0 minus 0.76. This we will get from the voltmeter. You're getting a value of minus 0.76. So this is the standard reduction potential of this half cell. And now taking the copper half cell and connecting it with She, and in that case the She is acting as anode and the copper half cell is acting as cathode. So E naught cell is equal to E naught cathode minus E naught anode. So that would be equal to 0.34. The value of the electrode potential value is 0.34, and this it's taken to be 0. So the answer is plus 0.34 volt. So this is the standard reduction potential of copper. So how do we represent reduction potential? See, Zn2 plus Zn. So this is the reduction potential of zinc, which is given the value minus 0.76 volt, and Cu2 plus Cu, which is the reduction potential of copper. But remember, when we take zinc and copper, which means the Daniell cell or voltaic cell, zinc is undergoing oxidation and copper ions are undergoing reduction. But here we are representing the reduction because we are talking about reduction potential. So we are talking about reduction. So Zn2 plus slash Zn, because from 2 plus it is going to 0 when we represent this way. So this represents what? Reduction. Same way Cu2 plus to Cu, again reduction is here. So this is the reduction potential. Suppose if you want the oxidation potential of zinc, how do we represent? Zn slash Zn2 plus, and this value would be plus 0.76 volt. Same way for copper, this is the reduction potential, and if you want the oxidation potential, how do you represent? Cu bar Cu2 plus, and this value would become minus 0.34 volt. So as I told you already, the electrode potentials are expressed as reduction potentials or as standard reduction potentials. So when we arrange these values in the increasing order of the reducing strengths to form a series, we call that as electrochemical series. In your textbook, you could see a tabular column written as standard electrode potentials or electrochemical series. In that, if you see, you could see the standard electrode potentials of different half cells arranged in the increasing order of their reducing strength. Now I'll show you a picture of that electrochemical series, not the entire picture, just few values written. Here I have written the first two and the last two in the series. So you can refer your textbooks for all the values. See here, the value is 2.87. This is for fluorine and cobalt, and it goes on for K plus potassium ion and lithium ion. So all these values written here in red are standard reduction potentials of the cells. So which shows the tendency to undergo reduction, which means the tendency to accept electron. So 2.87, 1.81, and as you move down it becomes negative. So it is in the decreasing order of the value. So remember one thing, these are the E naught values which are called as standard reduction potentials. And look at this sentence that I have written, smaller E naught value, which means more negative, which means it can undergo oxidation easily. So in the top of the series, they can undergo reduction easily. As you move down the series, they undergo reduction at a slower rate, which means they undergo oxidation easily. So in terms of oxidation and reduction, how can you define reducing agents and oxidizing agent? If the species has more tendency to undergo oxidation, it can act as what? Reducing agent. So as you move down the group, the tendency to undergo oxidation increases, which means the tendency to act as reducing agent increases. So that's what I've written here in this arrow, downward arrow. As you move, increasing strength of reducing agents, so they can act as reducing agents, which means they have tendency to get oxidized easily. That tendency increases, which means they have more tendency to lose electrons as you move down the series. As you move up the series, they are arranged in the increasing strength of oxidizing agents. So as you move up, the tendency to act as oxidizing agents, the capacity increases, which means the tendency to get reduced increases, which in turn can be said as the tendency to gain electron increases. So remember, smaller E naught value compared to minus 2.93 and minus 3.05, which is smaller, minus 3.05, which means more negative. So smaller E naught value or more negative value, they will undergo oxidation easily. So when they give you two values and when you are trying to compare that, if the value of one species is greater and one species is lesser, the one with the lesser value will undergo oxidation easily. The one with the greater value will undergo reduction easily. Now let's see what is the applications or use of these electrochemical series, what is the purpose of arranging them in this order, and what other details you can get from this electrochemical series. So the applications of electrochemical series. The first application is comparing reducing and oxidizing power. Reducing character means they have electron releasing tendency. Oxidizing power means they have electron accepting tendency. So the element placed higher in the series is a weaker reducing agent. Just now I told you, as you move down the group, tendency to act as reducing agent increases. So the element placed higher in the series is a weaker reducing agent. Now for example, there are two values, electrode potential values written, one for Zn2 plus Zn and this for Ni2 plus Ni. Look at the values. For this, for zinc it is minus 0.76 volt and for nickel it is minus 0.25 volt. Now the question is, which can act as a stronger reducing agent comparatively? So now look at the value. This is minus 0.76, this is minus 0.25. I've told you, smaller E naught value, which means more negative value, it can undergo oxidation easily. So they can act as reducing agent, better reducing agent. So comparing these two values, which value is the lesser value, which is more negative, minus 0.76. So zinc is a stronger reducing agent than nickel. So this is how we compare the electrode, standard electrode potentials to find out the reducing and the oxidizing power of the given species. Now the second application of this electrochemical series is predicting the feasibility of a redox reaction. You know what is a redox reaction? What is meant by feasibility? Whether a reaction can take place or not. So that can be found using the standard electrode potentials. Now see this example. Predict whether the reaction is feasible or not. They have given you a reaction Fe solid plus Ni2 plus aqueous giving you Fe2 plus NiS, which means solid, and they have given you E naught value of iron to be minus 0.44 volt and E naught of nickel to be minus 0.25 volt. So these two values indicate that who can lose electrons easily, which means who can undergo oxidation easily, the lesser value, which means more negative value. So comparatively, Fe has got more negative value. So Fe can lose electrons to Ni2 plus in the solution. So Fe has more tendency to lose electron comparatively and nickel has more tendency to accept electron. So what would be the reaction? You can look at this overall reaction, and based on these values you have to write the oxidation half reaction and the reduction half reaction. Now, which will be the oxidation half reaction? What is oxidation? Losing of electrons. Compared with these two, who can lose electrons easily? From the values we just decided, Fe can lose electron easily. So Fe losing electron is the oxidation half reaction, and Ni2 plus accepting electron is the reduction half reaction. And we know oxidation reaction takes place at anode and reduction half reaction takes place at cathode. Now see, Fe giving you Fe2 plus, and that would be plus 2 electrons, and Ni2 plus is taking 2 electrons and becoming Ni solid. So this is oxidation where Fe is changed into Fe2 plus, and this is reduction where Ni2 plus is changed into Ni. Now how will you represent this cell? And remember, whenever a question is asked in electrochemistry, if they give you the overall reaction, try to write the oxidation half reaction and the reduction half reaction, and also you have to represent the cell. And I've told you how to represent the cell. You have to represent the anode and then the cathode. Which is the anode reaction here? Fe changing into Fe2 plus. See, Fe, put a slash Fe2 plus, and salt bridge double slash cathode. What is happening at cathode? Ni2 plus is changed into Ni. So this is the cell representation. Now you have to find out E naught cell. E naught cell is equal to, what is the formula? E cathode minus E anode. What is the cathode here? This is the cathode, this is the anode. What is the E cathode value? 0.2 minus 0.25, and anode value is minus 0.44. So minus 0.25 minus of minus, which becomes plus. So you get a value of plus 0.19 volt. And remember, if the E naught cell that you're calculating is positive, then the reaction is feasible. So using the electrochemical series, you're finding out E naught cell, and from the E naught cell, you're predicting whether a redox reaction is feasible or not. I told you, E naught cell value, if it is positive, then the reaction is feasible. When the reaction is feasible, you have to relate that with the solution. For example, we say this reaction is feasible, which means Ni2 plus. Where can you find this Ni2 plus? In NiSO4 solution. For example, if you take NiSO4 solution, what will be present? Ni2 plus will be there. If you take a vessel made of iron, it is Fe. So if you store NiSO4 solution in Fe, what will happen? There will be a reaction, and Fe will be changed into Fe2 plus, Ni2 plus will be changed into Ni. So you cannot store a solution of nickel sulfate in a iron vessel. However, you can do the reverse. You can store FeSO4 solution in nickel vessel, because when this reaction is happening, the reverse is not going to happen. See, when you take the reverse reaction and try to calculate the E naught cell, you will get a negative value. So when you get a negative value, the reaction is not feasible. So you can safely store ferrous sulfate solution in nickel vessel, but you cannot store nickel sulfate solution in iron vessel. So this is another application of electrochemical series. And now the third application of electrochemical series is predicting whether a metal can evolve hydrogen from an acid or not. When you treat a metal with any dilute acids, that metal can displace hydrogen from the acid, and not all the acids will displace hydrogen. So to know whether a given metal can displace hydrogen from an acid or not can be predicted from the E naught values. See, elements lying above hydrogen. When you look at the electrochemical series, you have few values which have positive sign, and after that you will have hydrogen electrode potential, and below that you will be having negative values. So elements lying above hydrogen are weaker reducing agents, which means they have positive value, and elements lying below hydrogen are having negative values. So elements lying above hydrogen, which means they have positive value, they cannot lose electrons to H plus ion of acids, because when you take acids you have H plus ions, and elements lying above hydrogen are weaker reducing agents, which means they cannot lose electrons to H plus ions. That means those metals having positive electrode potentials cannot evolve hydrogen from acid, but those metals having negative electrode potentials can evolve hydrogen from acid. See, for example, metals like sodium, potassium, zinc, magnesium, aluminum, they have negative value. When you look at the electrochemical series, you can see they have negative value, and they are placed below hydrogen. So they can evolve hydrogen from acid because they are better reducing agents, and hence they are called as active metals. But metals like copper, mercury, silver, they have positive value and they cannot evolve hydrogen from acid, and they are called as inactive metals. So these are the applications of electrochemical series. Now let's apply these knowledge that we have gained now to few problems. So before we move into the example, please recall, when you are comparing two E naught values, which means standard reduction potentials, the smaller E naught value, which means more negative value, will undergo oxidation, which means that will be acting as anode, the other will be acting as cathode. Remember that. And second point, if the E naught value that you're calculating, which by applying the formula E cathode minus E anode, is negative, then the redox reaction is not feasible. If it is positive, then the redox reaction is feasible. Now look at this example. A cell is set up between copper and silver electrodes as follows. They have given you the cell representation. So this is the cell representation. Question is, calculate EMF. EMF is nothing but electromotive force, or you can call it as E naught cell. So again, they have given you the E naught value of copper to be plus 0.34 volt and E naught value of silver to be plus 0.80 volt. I've told you already, look at this representation. Cu2 plus to Cu is reduction. So this is reduction potential. Ag plus to Ag is also reduction. So this is reduction potential. For example, if it is represented as Cu bar Cu2 plus, the value would have been minus 0.34 volt. If it is given in such a way, then you have to change the symbol and use the standard reduction potential in the problems, not the standard oxidation potentials. But here no problem, they have given you reduction potentials only. So from the E naught values, you can predict which metal is acting as anode and cathode. See, this is more positive. This is less positive, more positive, which means this is a greater value, smaller value. So smaller value has more tendency to undergo oxidation, that can act as anode. So copper acts as anode, silver acts as cathode. So now find out the E naught cell. E naught cell is equal to E naught cathode minus E naught anode. This is what asked in the question. Calculate EMF. Now you know what is cathode and what is anode from the given E naught values. So which is the cathode? Silver. So what is the E naught of silver? 0.80 minus 0.34. You are getting a value of 0.46 volt. That is the EMF of this cell. And we are calculating that EMF from the standard electrode potentials of the half cells. Now look at the next example. So a cell is prepared by dipping a copper rod in 1 molar copper sulfate solution and a nickel rod in 1 molar nickel sulfate solution. The standard reduction potentials of copper and nickel electrodes are plus 0.34 volt and minus 0.25 volt. So they have given you a picture of how the cell is prepared and the reduction potentials also. So now the question is, which electrode will work as anode and cathode? What will be the cell reaction? How is the cell represented? Calculate the EMF of the cell. So they have given you the cell representation, the picture of how the cell is prepared, and they have given you the standard reduction potentials. And now they are asking you these 4 questions. So what is given? E naught of Ni2 plus Ni, which means standard reduction potential of nickel is given, and standard reduction potential of copper is also given in the question. Now let's try to answer one by one. First question, which electrode will work as anode and which will work as cathode? I told you smaller E naught value will act as anode because it will have a more tendency to undergo oxidation. And the one with more E naught value will act as cathode because it can have the more tendency to undergo reduction. So here minus 0.25 plus 0.34. Smaller value is 0.25. So nickel acts as anode and copper electrode acts as cathode. So we have answered the first question. Now moving on to the second question. What will be the cell reaction? You know, anode oxidation takes place and in cathode reduction takes place. So at anode, nickel solid is losing 2 electrons and becoming Ni2 plus 2 electrons. Usually it will be 2 electrons because plus 2 oxidation state is more stable for nickel and copper, and only for silver it will be 1 electron because Ag plus is more stable. So now Ni solid is changed into Ni2 plus and by losing 2 electrons, and here cathode reduction is happening. So Cu2 plus is taking up 2 electrons to become copper solid. So this is the anode half reaction, cathode half reaction, where the question is what will be the cell reaction, which means the overall reaction. So in the overall reaction, Ni solid plus Cu2 plus aqueous, these electron and these 2 electrons will get cancelled out, will give you Ni2 plus aqueous plus Cu solid. So this is the cell reaction. Now moving on to the third question, how is the cell represented? What will be the cell representation? I've told you anode and then cathode with the salt bridge. So in anode, nickel is changed into Ni2 plus. So Ni solid slash Ni2 plus aqueous, and they have given you in the question it is a 1 molar solution. So here in bracket you have to put 1 molar here for Ni2 plus, not for Ni, and this double line stands for the salt bridge. And for cathode, Cu2 plus is changed into Cu. Same way here in bracket you have to put 1 molar concentration. So we have answered the third question also. What is the fourth one? Calculate the EMF of the cell, which means you have to calculate the E0 cell. So EMF of the cell is equal to E0 cathode minus E0 anode. Cathode is copper and anode is nickel, and the values are given. So 0.34 for cathode minus 0.25, that gives you 0.59 volts. So that is the EMF of the cell. And from the E0 values you can answer any type of questions if you understand the concepts properly. Now let's move on to the next example. Read the question. Write the cell reaction that occurs when the following half cells are combined. So they've given you two reactions. See, both are reduction reactions. So they are combining these two reactions, and they are asking you what will be the cell reaction when these half cells are combined. They have given you the reaction, but you have to decide from the E0 values which will undergo reduction and which will undergo oxidation comparatively easily. So they have given you I2 plus 2 electrons giving you 2I minus. For that E0 value is plus 0.54, and for the next reaction, bromine plus 2 electrons giving you 2 Br minus, and again the concentration is 1 molar. E0 value is plus 1.08 volt. So comparing these two values, you know lesser E0 value will take place at anode while the other takes place at the cathode. So the lesser value is 0.54. So this reaction is going to take place at anode and this reaction is going to take place at cathode. But anode, we know what reaction occurs? Oxidation reaction. So the reverse of this reaction will occur at anode and this reaction will occur at cathode. See, 2I minus giving you I2 plus 2 electrons, oxidation occurring at anode, and here Br2 plus 2 electrons, this is accepting electrons, so this is reduction, giving you 2 Br minus is happening at reduction, cathode, because this is reduction. Now the overall reaction, 2 electrons and 2 electrons cancelling, and 2I minus plus Br2 giving you I2 plus 2 Br minus. So this is the cell reaction. So from the given E0 values, you have to decide among these two reactions which will undergo oxidation and which will undergo reduction, and then you have to write the oxidation half reaction and the reduction half reaction, and then write the overall cell reaction. So these type of problems will be asked based on this electrochemical series. But before ending this video, I just want to give you a few points about what will happen if you connect an electrochemical cell to an external potential. If you are applying an external electrical energy to the electrochemical cell, what will happen? When you take a galvanic cell, you are combining zinc and copper electrodes dipped in their respective salt solution. Zinc electrode and zinc sulfate solution, copper electrode and copper sulfate solution. And what is the EMF of that galvanic cell? 1.1 volt. And you can calculate that also from the standard reduction potential. E cathode minus E anode. Cathode is copper, anode is zinc. Cathode for copper, the value of E0 is 0.34 minus 0.76. You're getting 1.1 volt. And you know when you're connecting zinc and copper electrode in an electrochemical cell, which means a galvanic cell, what happens? What are the observations? Electrons will move from zinc to copper, and zinc dissolves from zinc electrode, and copper gets deposited on copper electrode. This is what happens when you look at a galvanic cell. Now what we are going to do, if you are going to apply an external potential, if external potential is applied, Ex, which means you are connecting it to a external potential where you are going to apply electrical energy. If the E external value is less than 1.1 volt, what is this 1.1 volt? The maximum EMF that can be obtained from this cell. If the potential that you are applying from outside is less than this value, then the reaction continues to take place, which was happening already. What was happening already? From zinc, the electrons are moving to the copper half cell, and flow of current is from copper to zinc. And the reaction, what reaction is happening? Zinc is undergoing oxidation and copper ions are undergoing reduction. So that continues as long as the external potential is less than 1.1 volt. If the external potential is equal to 1.1 volt, what will happen? The reaction stops. No more reaction will take place. So when the reaction stops, no current flows through the cell. Now, when you increase the external potential more than 1.1 volt, now when it is equal, the reaction has stopped. Now what you are doing, you are gradually increasing the external potential that you are applying to be greater than the EMF of the cell. What happens? Again the reaction starts, but it goes in the opposite direction. What will happen then? When the reaction is going in the opposite direction, the flow of electrons will be from copper to zinc, while current will flow in the opposite direction, which means copper will dissolve from the copper electrode into the solution, and at the same time zinc will get deposited on the zinc electrode. That was a non-spontaneous reaction. You know, right? Zinc is dissolving and copper is getting deposited is a spontaneous reaction which doesn't need any external energy. But the reverse reaction where the copper is getting dissolved and zinc is getting deposited is the non-spontaneous reaction. But now that has started to happen when the external potential is greater than the EMF of the cell. So when you apply an external potential greater than the EMF of the cell, you can conclude that a non-spontaneous redox reaction is made spontaneous. Okay, so remember this. When potential more than the EMF of the cell is applied, the non-spontaneous redox reaction will start to happen, which means the reverse will happen. Representing this cell is just like how we did with the electrochemical cell, but one small change will be you're connecting it to the external potential. Thank you.